Welcome to the first video on stochastic integration. So this video, we want to start constructing or understanding what it means. How a stochastic integral looks like. So we want to, construct this. We want to give a meaning to the expression that, okay, what is a suitable generalization of an integral now with respect to a Brownian motion, right? So we want somehow to define this object here, whatever this means. We usually use B for Brownian motion. So what we have here is, this is a Brownian motion as our prototypical example of a martingale. And this is a question, okay, what is the class of integrants? So this is somehow a suitable stochastic process, right? But we need to specify in this chapter as well, what f's are allowed as integrand. Okay. And well, first, let me recall the setting. So this is the setting as well I have seen before in the lecture. So we have completed underlying probability space, complete probability space. We fix the Brownian motion. So we have given a Brownian motion. Is Brownian motion. We consider the associated completed filtration to it. So this is the Brownian standard filtration. So it's complete, so all the null sets are included in FT, and the filtration is right continuous. So this is the Brownian standard filtration. And we assume, and okay, this is maybe different. Well, that makes it red. Our time horizon now is supposed to be, it has to be finite time horizon. You can extend this by localization arguments also for t to be infinity, but I don't want to focus on this. So I just assume that this is finite, all right? So my terminal time is finite. This just makes my life easier. Okay, so we want now to understand this object here. So we want to understand this object, which is our goal, in a reasonable way, right? So we know how this object looks if we have here some smooth path B, but if you have Brownian motion, we don't understand it yet. So as usual, what we want to do is we want basically to define the integral for simple integrands for which we immediately understand what it means, and then we want to slowly extend it to a more general class of integrants. Okay, this is chapter 3.1 in the lecture notes, called construction of the Ito integral. And it's called Ito integral because Ito was in the 40th the one who developed this theory, and of course it was afterwards extended quite a lot by several authors or researchers. But okay, for us, we stick here first to the basics and develop stochastic integration for the Brownian motion. Okay, what do I mean? We want first to write down something we understand, which gives the Brownian, this stochastic integral, the meaning we want to have, right? And something where it's not hard to define an integration process or the integral is if we consider space of simple integrals. So this will be denoted by h20. And what is it? So these are all f's, right? This should be my integrands, which map from the sample space omega t to r, one-dimensional. And what do we want? We want that it's given as step function. I mean, you have all seen step function in the construction of Riemann integrals. The only difference is now we have here random coefficients, right? So this step function means, okay, I have my random coefficients ai, which might depend, I mean, will depend usually on omega, and then I discretize the time horizon by a small step from ti to e ti plus 1. Okay, and now I want certain that my coefficient fulfills certain requirements. So the AIs are supposed to be ft1 measurable random variables. So I want that my step function is adapted to the Brownian standard filtration. I want that they are in L2, so they're square integrable. Well, okay, my time interval, so my partition of the time interval, okay, so given here by ti at t0 to t1 up to tn. Yeah. And I is 1 between n, and n is a natural number. Right, okay. So this is my space of simple functions, of simple integrals. So simple functions. Right, so this is how I refer to them. Okay, and if I have the simple function, I mean, we can define the integral, right? And this is, I mean, to define a reasonable integral, consistent with, for example, Riemann integration or our interpretation as capital process in mathematical finance. So the characteristic integral of simple function f in, so okay, let me, f given here is the sum, so this is the representation I choose. Right, s, so this is supposed to be an h20 is defined as, well, so let's call it I. So for integral of f is nothing else, I mean, than the sum of, yeah, well, so you sum over 1 to n minus 1, then you have ai, which might be your position in the market, and then the prime motion model, the price fluctuations. So this is a capital process we have seen at the beginning, right? So this is a simple left point Riemann sums, right? So you have your O constant, so your simple function is constant over the time interval ti and ti plus 1, and on this constancy interval you have always the value ai. So this is, we can refer to it as the integral from 0 to t of f omega s tbs. Okay, so this is, I mean, for this simple class of function, I mean, this class of simple function, to define what I want my integral to be, that's simple, and this is well defined. So here, but now you want to try to understand this integral operator and this integral in order to extend it to a larger class of integrals. Okay. what we want to do is to consider the space H0 as a subspace of L2, but now L2 on the product space of omega and the time interval 0 to t. And then on this product space, I also consider the product measure. And if I'm on this space, the natural norm I want to consider is, of course, the L2 norm. So if I take a function f in this space or in this L2 space, doesn't matter. So my norm on H2, and I drop here this 0, this is on purpose, and you will understand later why I want to do so. There's nothing else than the L2 norm on this with respect to this product measure. And this is nothing else than, let's spell it out, the expected value of the integral from 0 to t of f square. Squares can also make the square here, it doesn't matter. Yes. And then we normalize it to have a norm. And this works actually for all L and L2. So this norm, which is naturally, if we consider this H20 space as part of the bigger L2 space, this is the natural norm to consider. The good thing is, if I look at the operator, the integral operator, I, which maps a function from H20 to, let's say, L2, so to an L2 square integral random variable. Right? This is our standard L2 space. This turns out to be isometry. In particular, it's continuous. And if I have a continuous operator, then okay, we know there's a unique way to extend it, which we do later. But first, we need to formulate and prove this claim. And this is context of the next lemma 3.2, which is Ito's isometry in its simplest form, right? Okay, here we consider simple integrants of functions, so this is also what I want to refer as isometry, the simple version of it. We will later have, of course, a more general version, but here we need this. So if I take a function, step function, simple function in H20, what do we have? Well, we have that the H2 norm, which is just here the L2 norm on the product space, is nothing else than the integral operator applied to this simple function, which we know how to define. So this is a well-defined operator in H20, and then the L2 norm with respect to the P, right? So classical P norm. Okay, so that's, what an isometry is, right? So we have here two spaces. So this is the norm on this space, right? And this is the norm here on this space. Okay, so let's prove it. It turns out to be, I think it's surprisingly simple, because this is the foundation of how we want to develop each integration. It's proof. Okay, I have my simple function. Let's take an f, which is just given here my representation as before. So just to remind you how my f looks like. Which is a function in H20. First observation we have, if we calculate the H2 norm of f, what do we get? I mean, just to remind you on the definition, because it's rather new here, nothing else than the expected value of the integral from 0 to t of f square. Yes. And now, okay, since here, I mean, this is a simple step function, we can represent this as finite sum from 0 to n minus 1 of square, right? This is what comes out. So we square the AIs. And then we have the increments of in time. No? Okay. So what we did is we calculated the left-hand side of this claimed equality here, and now we calculate the left-hand side. Okay. So let's do this. What's the left-hand side? We want to calculate the integral operator applied to f, and then the L2 norm. And let me make here squares because I forgot here. Right? Otherwise, I need to normalize it. Here we go. All right. What is it? Okay, this is just the L2 norm of the random variable f applied, I applied to f. And this means you have here a square somewhere. Yeah. Okay. Now we plug in the definition. And that's the definition. Cool. I forgot somehow a square. The square. No, I didn't forget it. I forgot it. No, I forgot the bracket. Right. It's okay. So you have the square around the sum. And now we need to multiply it out. No, we don't need to, but we should. Otherwise, we're not finishing the proof here. So this you have get the double sum from AJ, from I and J, from 0 to n of AI, AJ, and then the increments of the Brownian motion of T with respect to TA, and the same with J's. Okay. And now we order it a bit. So first look at the diagonal. So what we do is, I mean, this is a matrix, right? I mean, you have all the products between I and J from, so these are n plus 1 square summands. And the first, okay, we look at the one on the diagonal. So these are from 0 to minus 1 of the Brownian motion Ti plus 1 minus Ti, Bti square. And now here I directly insert like use the tower property, and that this here is Fti measurable. Okay. And now I have twice, let me order them of all the terms of the diagonal. So let's assume, I mean, let's order them. This is why the 2 is coming. So we assume that I is strictly less than J, and this means we order them in this way. And again, AJ, same trick. So we get out the one Ti is smaller, so we get them out, and we sneak in the conditional expectation with respect to Tj. And again, we use, I mean, these terms here are all t or j measurable. Cool. Okay. Okay, so what else do we learn? We have that the Brownian motion is a martingale. So this means this is just 0. So the second term, so all the off diagonal terms disappear. That's cool. Makes our life much simpler. So we have only the sum from j over I from 0 to n minus 1. And what do we see here? I mean, okay, we have a square. So the Brownian motion is in the increments of the Brownian motion are independent from this sigma algebra. So what we have here is tj plus 1 minus tj square. But again, we know what this is. This is nothing else than the difference of ti plus 1 minus ti. Okay. Cool. And okay, let me rewrite it so that we see that we are done. Oh. So this is the sum from I from 0 to n minus 1 of the expected value of ai to the power 2 multiplied with the increment of ti plus 1 minus ti. Right. And now this was the left-hand side, right? So we calculate here the left-hand side and here the right-hand side. Now we see that if we look at this, so this is the expression for the left-hand side, and this is exactly the same as we got for the right-hand side. So we are done. Done. Okay. All right. Cool. So we already, I mean, this was rather simple proof to show this Ito isometry in the simplest version. So we have the isometry between the H2 space and the L2 space. Before going on to extend it, let me give you one remark. As I don't give it. I will not give it, this remark a number because I'm not further using it. So what we actually have shown reads as this isometry is just telling us that if I look at the expected value of the integral of f squared, yes, and now I write the E2 integral a bit fancier. I just write it with respect to the quadratic variation of a Brownian motion. And I recall, I mean, keep in mind, I mean, this is just S. So, this is nothing else when this lemma 3.2 is nothing else than the expected value of the square of the integral of f as the Brownian motion. At least for all f in H2. Okay. So just as a remark, so if for a martingale, let's say continuous martingale, MT, we would get nothing else than f squared. Now we replace the quadratic variation of a Brownian motion with the quadratic variation of the general martingale, general continuous martingale. And then we would have here just the L2 norm of the simple function integrated with respect to the martingale with the obvious definition as Riemann sums. Okay? Assuming that everything is well defined. What does it mean? Okay, we just need at the end that. So if you have a uniformly in L2, this all works. Okay. So I mean, you see why the quadratic variation is so important to develop E2 integral, even if we haven't seen it directly for the Brownian motion. The only reason why we haven't seen it is because we were hiding here the Brownian motion with respect in this ds integral. But we will later see how we end up with such an equality. Okay. So thank you for watching the video. In the next one, we will then extend the E2 integral from simple functions to more general class.